right, good afternoon, everybody. Welcome, good to see you. Hope you all have started your attack labs. Everybody started? Be a good time to start, I think. Anyway, I hope you're enjoying it. That's a new one this semester that's, I think, really interesting and modern and current. Okay, today we're going to talk about something called the memory hierarchy. Now, so far in the class, we've thought of memory when we're looking at our assembly language programs. We've thought of memory as an array of bytes, just a big array of bytes that we can access with an index called an address. But in actuality, the memory system is a very complex hierarchy of devices that provides this abstraction of this large linear array. And so today we're going to look at how memory hierarchies are built and why they're built the way they are. And what we'll see is that this sort of beautiful confluence of the properties of storage devices and the properties of programs come together to create this beautiful design called a memory hierarchy. So we're going to quickly kind of do a high-level tour of storage technologies and trends. We're not going to go into a whole lot of detail. The point in looking at the properties of these technologies is that there are some fundamental properties that determine their performance and their speed, and determine limits on their performance and speed. And so I want you to have just some high-level idea of what those properties are. And then we'll look at a property of programs called locality of reference, and we'll see how that locality and the properties of storage devices come together to suggest this design of memory systems as a hierarchy. Okay, so we'll look at memories first. Now the workhorse memory is called a random access memory, or RAM. It's traditionally packaged up as a chip, and then you put multiple chips together to form your main memory. And there's a basic storage unit called a cell, where each cell stores 1 bit. Okay, now there's a RAM comes in 2 varieties. There's SRAM and DRAM, and they're distinguished by the way that those cells are implemented. So in an SRAM, requires it's more complex than DRAM. It requires like 4 to 6 transistors per bit, whereas DRAM only requires 1 transistor. Okay, so you'll see that SRAMs are going to be more expensive, lots more expensive, because they're more complex. Each cell is more complex, but they're also much faster, like 10 order of magnitude faster than DRAMs. And they have there's some other properties too, like DRAM constantly needs to be refreshed. If you don't hit it with a voltage, it loses the charge. Whereas DRAM, while it needs to be plugged in and have an electric charge, it doesn't need to be refreshed. SRAM's a lot more reliable than DRAM, so there's less need for error detection and correction. And so because of this difference, right, the SRAMs are costlier, smaller, and faster than DRAMs. We find SRAMs being used in these small, fast memories on chip called cache memories. Okay, and we're going to learn all about those on Thursday. And then DRAM is the workhorse used in main memories and the frame buffers associated with graphics cards. Now, DRAM and SRAM are volatile in the sense that if they're powered off, they lose all the information, right? So this is why when you turn your computer off, you lose everything in your memory, and when you turn it back on, you have to sort of reload everything from your disk. There's another kind of memory called a non-volatile memory, which retains its information when it's powered off. And there's a whole bunch of these things, so-called read-only memories. So the generic name for these non-volatile memories is read-only memories or ROMs, and there's a whole bunch of different kinds, sort of going back in time. The original read-only memories were ROMs, and they could only be programmed once when the chip was produced. And then over time, gradually, over a period of like 20 or 30 years, there were improvements in the way that ROMs could be programmed and in how they were erased, so they could be reprogrammed. What we have today, the modern form of read-only memories is called flash memory, which provides the capability of erasing. You can erase just chunks of the flash memory called blocks. And then the downside is that these things wear out after about 100,000 erasures. Okay, so you can erase and reprogram 100,000 times, and then it's you're bricked. Now these non-volatile memories show up in so-called firmware, which is software that's programmed into a ROM. And you see those in the BIOS of computers. So when you power on your computer, the very first instructions that execute are stored in a ROM, right? Have you ever wondered, like, where do those things come from? So they're stored in a ROM, and then there's a boot process where gradually more and more information and instructions are loaded into memory. I/O devices have little computers in them called controllers. These controllers consist of instructions and data that are stored in ROMs, and you see them all over the place in these solid-state disks that to the system look like a rotating disk, but they're built of flash memories. Okay. And you see these in thumb drives, smartphones, tablets, and laptops, and they're even starting to show up in servers now. So the memories are connected to the CPU using sort of wires that are collectively called buses. Okay, so data flows across the wires back and forth from we have the CPU chip, and it consists of a register file. These are the general purpose registers, RAX, RDI, and so on. And there's an arithmetic logic unit that reads and writes data from the register files and then manipulates that data in some way by doing some kind of arithmetic operation or some logical operation. And if instructions need to access memory, so if you're doing a move instruction that reads or writes to memory, then that's handled by a bus interface, which is connected to what we'll call a system bus. And then that's connected to an I/O bridge. And this is another collection of chips. Intel calls this, what I'm calling the I/O bridge, they call the chipset. Okay, but it's a collection of chips separate from the CPU chip. And then the I/O bridge is connected to another bus called the memory bus, which connects to main memory. Okay, now this is kind of an abstraction. I don't want you to take this too literally, but it gives you the idea of how information flows in the system. Okay, modern systems use proprietary bus designs, and they're very, very arcane and increasingly complex. So we're just going to use a fairly simple abstraction for these bus architectures. Now suppose you do a load operation like move Q the 8 bytes at address A into RAX. Okay, so we call that a load because we're loading from the point of view of the CPU. We're loading data into the CPU, or we're loading data from memory into the CPU. So when the CPU executes a move instruction like this, it first places the address of A on the memory bus, and then the main memory senses that address, and it reads the contents, the 8 bytes at address A. So it retrieves the 8-byte word from address A and places it back on the bus. Those bits travel through the I/O bridge to the bus interface. And then the, the CPU reads the word X from the data word X from the bus and then copies it into register RAX. Okay, so it's now writing is similar. Again, so here we're doing a move instruction, move Q from RAX into address A in main memory. Okay, so the CPU starts as before by placing the address A on the bus. Main memory reads that address and then it waits for the data to arrive on the bus. So the CPU then places the contents of RAX on the bus, and those contents travel across to main memory, which then reads that word from the bus and stores it at address A. Okay, so the point of all this is that operations that occur, reads and writes of registers, because the register file is very close to the ALU, these happen on the order of a few cycles. Okay, the register is very close to the ALU, so those operations are happen very quickly. Whereas memory is actually, this is a set of chips that are very far away, relatively speaking, from the CPU. And there's a lot going on if you have to read or write memory. You have to do multiple operations on the bus. Data has to travel, propagate across that bus. All this stuff takes time. So memory operations, reads and writes, are typically maybe 50 nanoseconds, 100 nanoseconds, whereas operations that occur between registers are sub-nanosecond. Okay, are on the order of, so you're talking about 1 to 2 orders of magnitude difference if you have to go off chip to retrieve something from memory. Okay, so that's the first sort of big takeaway item about memory systems. Now, another popular storage technology is rotating disks. And I don't know if you've ever torn one apart. They're kind of interesting. There's a series of platters. Each platter is coated with a magnetic material. And then bits, ones and zeros, are encoded in that magnetic material. And then there's this arm that it's hinged right here. And then it floats over the platter. So it floats on a thin layer of air over the platter, and there's a read-write head at the very end that can sense the changes in the magnetic field that encode the bits. Okay, so these platters are spinning around like counterclockwise like this, and this arm can go back and forth. So there's a lot of mechanical gear. So this is all mechanical. So the mechanical nature of a rotating disk means it's going to be slower, right, than DRAMs and SRAMs. And there's also electronics, it's like a little computer in firmware that actually controls the operation of this drive, like controls how this arm goes back and forth and controls how the data is read off of the read-write head. So just in a little more detail, we can think of these disks consists of platters. Each platter has 2 surfaces, a top and a bottom. And then each surface consists of these concentric rings called tracks. And then each track consists of sectors which contain the data. So typically 512 bits, or I'm sorry, bytes. And then these tracks are separated by gaps these gaps, like right here, that don't contain data. Now, platters are aligned on top of each other, on this spindle. And so tracks that are aligned on the different surfaces, such as this track here, the collection of those tracks form what we call a cylinder, okay, because it has this cylindrical shape. Now, the capacity of disks is the number of bits that can be stored, and vendors all disk vendors use, they quote the capacity in gigabytes, but where a gigabyte is 10 to the 9th bytes, right, instead of 2 to the 20th, okay, like you would expect. So I'm not sure why they do this, but it allows, by quoting their capacity in gigabytes, in 10 to the 9th bytes, it's a bigger number, right? So it looks better. It looks like there's more information. It's a little, I don't really know why they do it, but I think that's why it is. And it's, so it's one of those little bit annoying things that we just have to just know about and get used to. Now, the capacity is determined by two independent technology factors. One is the recording density, so that's how many bits can you pack into a single sector, or at least a portion of a track. And then the track density, which is sort of how close can you put those tracks together. And then the product of those two is what's called the areal density, and that determines the overall capacity of the disk. So the higher the areal capacity, the more bits you can squeeze onto that surface. Now, in the old days, when areal densities were fairly low, each track on the surface would have the same number of sectors. Okay, so there was a constant number of sectors per track. So now what happens as your tracks go from the, near the hole by the spindle as they move outward, right? If you have the same number of sectors with the same track bit density, the gaps between sectors are going to get bigger and bigger as you go out, and you're going to be wasting more and more of your space. So when areal densities were fairly low, this was okay, but after a while it just became not okay to waste that much room. So what modern systems do is they partition the tracks into these so-called recording zones, where each recording zone, such as this right here, each recording zone has a constant number of sectors. So each track in a recording zone has the same number of sectors. And of course, as you move outward, if you move outward in the recording zone, you're going to have bigger and bigger gaps. But then you start a new recording zone that will have more sectors per track. And then within that, so you can see in this outer zone, you have more sectors than you do on this inner zone. Okay, so that's a way to kind of deal with that, sort of that growth in the gaps, to keep it from getting too large. And so because we don't really have, the number of sectors per track isn't constant, we'll use the average sectors per track across all recording zones when we do sort of our capacity estimates. Okay, so as you can imagine, the formula for computing the disk capacity is fairly straightforward. It's the number of bytes per sector times the average number of sectors per track times the average number of tracks per surface times the number of surfaces per platter times the number of platters per disk. Okay? Now let's look at how disks work. So these surfaces are spinning at a fixed rotational rate. Now a typical rate, maybe 7,200 RPMs, is a fairly common rotational rate. So the disk is spinning around. You can see this. I'm pretty proud of that. So it's spinning around counterclockwise. And then the arm moves radially. Here we go. The arm moves radially, and it can go over any of the tracks. Okay. All right, that's enough. Okay. Now, when you have multiple platters, each one of these, there's actually multiple arms, and there's a read-write head on each surface. So if the platter has if each side of the platter is coated with this magnetic material, then you have a read-write head on each side, and then these are all connected and they kind of move together. Now, originally these read-write heads they were rigid, right? Because the track densities weren't that high, so they could just sort of like, and even though the tracks didn't align perfectly, they could just sort of, they could still cover the read-write heads could still cover the tracks with these fixed arms. But nowadays the densities are so high that the controller can actually move the read-write heads a little bit so that it matches up with all of the tracks on all of the surfaces. Right? Okay, so let's look at how this works, how we read data. So we have our, this is our arm, and the tip of the arrow is the read-write head, and it's positioned, and the platter is rotating counterclockwise, and it's positioned just ready to read the blue sector. So as the blue sector spins underneath the read-write head, it senses those bits and sends them up to the controller, which passes them back up to the CPU. And now the CPU has requested that the disk, it's requested the red data from the red sector. So we have to take, the controller takes that read-write head, moves it back to red's track, and then waits for it to spin around and to the read-write head. And then it reads that red sector. Okay, so when we so there's really three components going on here that determine how long it takes to read one of these sectors. When we moved the head, that's called a seek. When we waited for the red track to sort of rotate around, that's called the rotational latency. So however long it takes, on average it'll be half of the time it takes for the entire to circle all the way around. And then there's the data transfer, which is sort of how long it takes for that track to pass under the read-write head. Now the reason it's important to know this is that these three components, you add them together, and that's your average time that it takes to access data. That time is dominated by the seek time. So seek times are measured in milliseconds, right? So we're moving this head. There's a servo that has to fire up, and there's actual mechanical motion. And that takes time. And it's on the order of 3 to 9 milliseconds. And this has been true for decades, right? So this value is not changing, right? There's just sort of fundamental mechanical limits that make it very difficult to decrease this value. Now the rotational latency, the time that it takes to spin around, we'll call that the t-average rotation, and then the time it takes to read the bits we'll call t-average transfer. Okay, so we have t-average seek, which is this seek time, rotational latency, and transfer time. And now if we just take some typical numbers and plug those in, you see that our seek time is on the order of milliseconds. The rotational rate is also on the order of milliseconds, right? So there's also mechanical limits in how fast you can spin these around. The access time and the transfer time is very small. So it's orders of magnitude smaller because you just have to read the bits that are in one sector. Okay, so if you look, you can see that the total access time is dominated by seek and rotational latency. So, a good rule of thumb just for sort of estimating how long it takes to read from a disk is just take twice the seek time, and you'll be pretty close. And basically, the transfer time is you get that for free. Now, here's the important thing to know about disks. SRAM access time's about 4 nanoseconds to get a double word. DRAM is about 60 nanoseconds. Right? So DRAM is about an order of magnitude slower than SRAM. But disk is 40,000 times slower than SRAM. So that's 4,000 orders of magnitude difference. That's huge. And it's 250 times orders of magnitude slower than DRAMs. So there's a big gap between DRAM and SRAM, and there's an even bigger gap between disk and other memory types. Now, modern disks present a much simpler view than this track, cylinder, sector geometry. So modern disk controllers actually present to the CPU, they present the disk as a sequence of logical blocks, where each block is a multiple of a sector size. So this, in the simplest case, a block is, just think of a logical block as one sector. And then blocks are numbered starting at 0, and they just go all the way up to some large number. And then the disk controller keeps the mapping, maintains the mapping between logical blocks and the actual physical sectors. So as in the old saying is, most interesting ideas in computer science involve some form of indirection. So this is a level of indirection that provides this mapping between logical blocks and physical blocks. So it allows disk controllers to take some cylinders and reserve them as spare cylinders that aren't mapped to any logical blocks. And then if one of the sectors goes bad in a cylinder, the disk controller can just copy the data over to a spare cylinder and then just keep going, right? So this is why your formatted capacity is less than sort of if you counted the number of actual cylinders on the disk, your formatted capacity is less than the maximum capacity because some of those cylinders are being reserved for failures. Now, devices like disks are connected to the CPU and the memory via the I/O bridge over another kind of bus called an I/O bus. What I'm showing you now is actually not representative of modern systems. It's representative of what was called the PCI bus about 5 years ago. Modern buses now are the PCI bus is a broadcast bus, meaning it's just a single set of wires. So if any device changes the values on those wires, every device on that bus can see those values. Okay. That's called a broadcast bus. And it's the simplest kind of way to hook things together. Modern systems use a bus structure called PCI Express, which, although it has the word PCI in it, it's completely different. It's point-to-point. So devices are connected by a set of point-to-point connections arbitrated by some kind of a switch. And we won't go into it. It's the same idea. It's a much more efficient design. It's much faster, but it provides the same capability. Mainly, it just attaches. It allows you to attach all of your devices to your CPU. So just think of this bus as this sort of a single set of wires, where each wire carries a bit, and every device attached to it can see all the values of all the wires. And so there's some devices that are just built directly into the motherboard and they attach to the bus. Like, disks are just plugged directly into sockets on the motherboard, and your graphics adapter and the USB controller. And then the system presents an interface so you can plug things like mice and keyboards into the USB controller. And then there's expansion slots that connect to the wires in the bus that allow you to add other devices, like maybe network, if you want to put a network adapter in there. Now, what happens when we want to read a disk sector? Well, the CPU initiates this read by writing a triple. So it writes 3 different values. It writes a command, like say read. It writes a logical block number. So I want to read a logical block number. And I want to place the contents of that logical block at a certain address in memory. Okay, so it's a command, logical block number, and a memory address. The disk controller reads whatever sector corresponds to that logical block. So we'll assume that logical blocks consist of one sector. And then it does this interesting thing. It copies it takes control of the bus, and it copies the data. This is the disk controller now. Copies the data across the I/O bus, through the I/O bridge, and directly to main memory without ever notifying the CPU. So the CPU is completely oblivious to the fact that this transfer is going on. And then once it's transferred the data to main memory, then it notifies the CPU using this mechanism called an interrupt. So it actually asserts a pin on the actual CPU chip itself. So it changes the value of that pin from 0 to 1. And that triggers an interrupt, which notifies the CPU that sector's been copied. Okay, so then the CPU, there's some program somewhere waiting for that data to be read into memory. So now the CPU can execute that program and deal with that memory. So what this mechanism allows, and the reason they do this is because disks are just so god-awful slow. Within 10 milliseconds, a system could be executing millions and millions of instructions. The CPU could be executing millions and millions of instructions. It would be a terrible waste if the CPU waited for that data to come off the disk. So what it does is it issues this request to the disk controller, and then while that really slow, laborious process is going on, the CPU can be executing other instructions and doing other useful work. Okay. So this is really essential to sort of getting reasonable performance and from keeping this really slow disk system from slowing the system down. Now there's another interesting high kind of disk called a solid-state disk, which is kind of halfway between rotating disks and DRAM memories. And a solid-state disk to the CPU, it looks exactly like a rotating disk. It has the same socket, plug. It has the same physical interface. It has the same packaging. Okay, it looks like a rotating disk. But instead of having all these mechanical parts, it's actually built entirely out of flash memory and firmware that acts as the controller. So inside of a solid-state disk, there's a firmware, a set of firmware called the flash translation layer, which serves the same purpose as the disk controller does in a rotating disk. And then the memory itself, the data can be read and written from the flash memory in units of pages, which depending on the technology can be 512K bytes to 4K bytes. And then a sequence of pages forms a block. Now these blocks are different from the logical blocks that the CPU does. So it's kind of an unfortunate overlap of terms. But the trick is, or I guess the limitation is that data is written in units of pages, but a page can only be written after the entire block has been erased. Okay, so that seems kind of weird, but that's the way it works. So what that means is if you want to write to a page, you have to find a block somewhere that's been erased. You have to copy all of the other pages in your target block over to that new block, and then you can do the write. Okay, so you can see that writes now become fairly complex operation. Reads, you can read anything. And then, like all flash, so it's kind of inefficient, right? Because you're writing one page. But to do that, you have to sort of copy all the other pages in that block, and you have to erase the whole. And then when you're finished, then you erase this block so it can be used for other writes. Yes. So eventually, after 100,000 repeated writes, these wear out. Now, the flash translation layers in modern systems do all kinds of fancy proprietary algorithms to sort of extend the life. They use caching and various tricks to extend the life of these SSDs. So in practice, it's not really a problem, which I'll show you in a second. So the performance characteristics of SSDs, now you can think of a typical hard drive, you might be able to get, when I measure them, when I measure my drives, maybe 40, 50 megabytes per second, that would be a typical rate. Okay, these SSDs are 10 times faster than that. So for sequential reads, you can get about 550 megabytes. Sequential writes are a little bit slower. Random access, whether you're reading or writing, is a little bit slower than sequential access. And as we'll see, this is fairly common. It's in memory systems, it's almost always better to do things sequentially than to jump around. And random writes are slower because erasing takes about a millisecond, right? So now we're back up to that millisecond range, which is slow. And as I mentioned, if you modify one page, all the other pages in that block have to be copied. Now, earlier SSDs had a huge gap between random writes and sequential reads. But because of sort of improvements in the flash translation layer, these aren't really that difference, right? Reading and writing, writing is slower, but they're doing all kinds of interesting, amazing things to get these numbers fairly close. Okay, so when we have a model of SSDs, we really don't need to distinguish anymore between reads and writes. Okay, so SSDs, because they have no moving parts, they're faster, they take less power, they're more rugged, which is why they're good for thumb drives and iPods and things like that. But they have this potential to wear out, which could be a problem, but in practice it's not. For example, Intel guarantees that you can do 128 petabytes of writes before your SSD is no longer good. So that's a lot of data to write. I mean, think about how many years it would take to write that much data. And as of 2015, as of now, they're a lot more expensive per byte than rotating disks. So rotating disks are much bigger, but they're slower. SSDs are smaller and they're faster. Now, if you look at the performance characteristics of these different storage devices relative to CPU, over time you get this really interesting graph. Now this graph shows on the y-axis access time in nanoseconds in a log scale. Okay, so each one of these, each change in units, like from 1,000 to 10,000, represents an order of magnitude difference in access time. On the x-axis, I've plotted time going from 1985 to 2015. And then I've plotted the access time or the cycle time of the access time of these devices, disk, SSD, DRAM, and SRAM, and the cycle time of processors. So let's look at, on the bottom we have the cycle time of processors over time. And what you see is it's going down at this sort of exponential rate from 1985 to 2003. There's a doubling basically every 18 months or 2 years in clock frequency and a resulting halving of the cycle time over this 18-month to two-year period. So what manufacturers did until 2003 to make their processors faster was they would just double the clock frequency. They decreased the feature size of the chips that they were making, and that would allow them to put things closer together and then increase the clock frequency by a proportional amount. Now this all ended. 2003 was an interesting year in computer history because of this. There's this sort of unfortunate property that the power that you consume is proportional to your frequency. Okay, so the more power, the higher the frequency, the more power you consume. By 2003, the processor that Intel was getting ready to ship was going to burn about 800 watts of power. Think about 800-watt light bulbs inside your laptop. And I actually saw an early prototype of one of these devices. And the heat sink to absorb the power from the chip was about this big. It was about 4 square inches. It was a giant thing just sitting on the motherboard. So that's what we say is that processor design hit the power wall in 2003. They could no longer just continue to increase clock frequencies to get faster, to make faster computers. And what they had to do after 2003, instead of increasing the clock frequency, instead of doubling the clock frequency, they put more processor cores onto the chips. So now they subdivided a CPU chip into individual processor cores. Each one could execute its own instructions. Okay. And then, and by running in parallel, you could do more effective work. So the effective cycle time could continue to go down. So what I've plotted here on the bottom is the effective cycle time. So basically the cycle time divided by the number of cores. So here in 2005, the first systems used 2 cores. So now you can run 2 independent threads or 2 independent programs. And currently it's about 4 cores. Server class systems, you can get 8 cores. And there's even some 12-core chips. So in the future, what's going to happen is that the clock frequencies are going to stay fairly constant. So you can see the cycle times they actually increased a little bit here, and then they're slowly going down, but it's generally flat. And so the only way to really get more performance going forward is to increase the number of independent cores. And that's just the way it's got to be. Now here in the black circle, the second line, I've plotted the access time for SRAM over time. And you can see that SRAM is tracking CPU pretty good. And it's an order of magnitude slower, but it's tracking the CPU performance pretty well. DRAM, you can see there's a huge gap between the CPU and the DRAM, several orders of magnitude. And in the last few years, DRAMs have gotten a little better, but they've proven surprisingly difficult to make faster. SSDs are kind of in between disks and DRAMs. And then disks up here, you can see at 1 million nanoseconds, that's a millisecond. So you can see disks are sort of in this sort of millisecond range with access times. And they've gone down a little bit, but not really too much. So the point I want to make is that there's this huge gap between DRAM, SSD, disk, and CPUs. And in some cases, it's even getting worse as time goes by. So that's a problem, right? How? Our programs all need data. Our data is stored in memory and disk. So if our computers are getting faster and our storage devices are staying relatively the same or relatively slower, then we've got a problem, right? Increases in computer performance it'll be hard to make our programs run faster because we'll be limited by the time it takes to access the data. Okay, so that's sort of the fundamental problem that we have to deal with. And it turns out that the key to bridging this gap between the CPU and memory is this very basic fundamental property of programs called locality. Okay? And so this is an essential, sort of fundamental, enduring property of programs. So we say that so programs have this property called locality. And what this means is that, I'm sorry, I have to read it because it's really accurate definition. So programs tend to use data and instructions whose addresses are near or equal to those that they have used recently. Okay, so if a program accesses a data item the chances are very high that it's going to access that data item or a nearby data item sometime in the near future. Okay. That likelihood that the program is going to access that data item or a nearby data item in the near future is this property called locality. So we just typically distinguish two different kinds of locality. Temporal locality is the property that recently referenced items are likely to be referenced again in the near future. Okay, so if you read a variable, chances are you're going to read that variable again. For example, suppose you're summing into a variable inside of a loop. Each loop iteration, you're going to access that variable. Okay. Spatial locality is the tendency for items with nearby addresses, that items, if we access one item, chances are high we're going to access a nearby item. Okay. So let's look at this little snippet of code and see if we can identify all the different kinds of locality in this code. So we have two different kinds of references. There's data references, and then there's instructions, right? So we're reading instructions out of memory, and those instructions are referencing data. Okay. So first of all, notice that we're referencing the elements of an array in succession. So we're increasing I by 1 each time, and then we're incrementing I each iteration through the loop, and we're reading AI. Okay, so this is called a stride 1 reference pattern. The stride is how much we're incrementing this index. So since we're incrementing it by 1, we call that a stride 1 pattern. So what kind of locality is these repeated references to AI? Spatial or temporal? Spatial, right? Because we're accessing nearby items. Okay, what about the referencing this variable sum inside the loop? That's temporal. Now, what about instructions? So we're referencing, each loop iteration, we're executing a sequence of instructions. So what kind of locality is that? Within each loop iteration. No, that's spatial, right? Because we're just executing a sequence of instructions within each loop iteration. But then we cycle through the loop repeatedly. So each loop iteration, we're going to access each of those instructions that we accessed the previous loop iteration. Right? So we go up, and we're just going to keep executing the same assembly language instructions that implement this loop body. Now, in this simple example, it's probably this one instruction. But in general, your loop can have multiple instructions. Now, what I claim to you, and one of the main sort of points of this whole course, is that as a professional programmer, it's an essential skill that you be able to look at code and get a qualitative sense of its locality. Because as we'll see, good locality turns into good performance, the way that systems are built these days. So as a programmer, it's very important for you to be able to kind of look at code and get some qualitative sense. Like, that's pretty good locality. That's terrible locality, right? And what you want to do is avoid the terrible locality in your code. So let's look at a simple example here to see what I mean by this. So what I'm doing is I'm taking an array, a two-dimensional array A, with m rows and n columns. And within a doubly nested loop, iterating on I and j, I'm summing the elements of that array. Okay, it seems this is a very simple operation. What could go wrong, right? So it turns out if you write this code to have bad locality, it'll run order of magnitude slower. Okay. So just look at this. If you look at this, do you think this has good locality or bad locality? I mean, let's look at with respect to the accesses of A. Good or bad? Well, so how is A laid out in memory? Right? It's row-wise, right? So C lays out arrays row-wise. So all the elements of the first row, followed by all the elements of the second row, followed by all the elements of the third row. Okay, so how are we accessing this array? We're accessing Aij, and we're varying j the fastest. So we hold I constant, and then we vary j, and then we access so we hold I constant to access row I, and then we vary j to access all the columns in that row. Okay, so and then we increase, and then we go back and increase I. So now we're accessing the next row. Okay, so if we were to look at the addresses of Aij, the sequence of addresses that are being read, those would correspond to a stride 1 access. And so we'd be accessing all the elements of A sequentially in order. Okay, so that's really good spatial locality, right? That's the best you can do. Now what about, and then we have temporal locality on some, so that's good. Right? So everything about this is pretty good. So this is the good case. Now what about this? What I've done, I've taken the same program and I've just inverted the loops. So I loop on j first, and then on I, and then I just have the same inner loop body. Now what does that do to this? What does that do to the spatial locality of our accesses of A? Yes?
Terrible spatial locality.
Terrible, because it's going. You should be offended when you see this. This is awful. But it's terrible, right? Because look at, so we're holding j constant, and then we're iterating through the jth element of each row. So that's skipping. We have n elements in each row. So we're doing a stride n access through memory. So we're going like this, and then we're incrementing, then we're incrementing the column by 1, and then we're doing this again. So it's terrible spatial locality. This is the worst spatial locality we could get. Now let's look at a 3-dimensional array. And let me pose the following question. Can you, based on this sort of qualitative idea, this idea that you want to try to get a stride 1 reference pattern. Okay, so how would you permute these, given this inner body, A, K, I, J, how would you permute these loop indices to give a stride 1 reference pattern? K, that's right, Kij is right. So in general, what we want to do is we want to going from right to left, we want those indices to be changing the fastest. So we want K and I to be held constant, and then we want to change J. Then we want to increment I, and then for that value, those values of K and I, we want to sequence through all the values of J again. Okay. Okay, so we've looked at properties of technology, of storage technologies, and there's this sort of basic, sort of fundamental principle that cheaper storage, bigger storage, higher capacity storage is cheaper. Right? More expensive storage is smaller, right? Because we just don't have enough. We can't spend enough money. There's this gap. There's this gap between our storage devices and the CPU that, at least in the case of disks, are getting bigger. And we have programs that exhibit locality. Okay. So these three things, these properties of storage technologies and properties of our programs, complement each other in this beautiful way to suggest and inform the design of our storage systems. And this design is something called a memory hierarchy. Okay, here's the idea of a memory hierarchy. You layer, instead of a flat memory system, you create your memory system as a hierarchy of devices. And at the top of this hierarchy, you have your smaller, faster, and more expensive storage devices. So at the very top, you have registers, which can be accessed within one cycle, right? One instruction, while that instruction is executing, can access read and write into a register. Okay, so registers are at the top of the hierarchy. But because those are in custom silicon, they're very expensive, right? The fabrication plants to make processors cost billions of dollars. Okay, so this is the most expensive. And because of that, it's also the smallest. We've only got 16 registers at the top of the hierarchy. Now, below that, we put one or more SRAM memories. Remember, SRAM is faster. It's the fastest kind of memory. So we put one or more so-called caches, cache memories built out of SRAM in the processor chip itself. And these caches, because they're made out of SRAM, they're on the order of megabytes in size. Okay, they're much bigger than registers, but they're megabytes. Okay, which, if we look, and then beneath that is our main memory, which is built out of DRAMs, and those can be gigabytes, tens of gigabytes on modern systems. And then below that is our local disks, and we can even have lower layers like web servers that are storing, if we're storing stuff on Google, that you can think of that as just part of our hierarchy. Now here's the key idea in a memory hierarchy. Each level in this hierarchy holds data that's retrieved from the next lower level. Okay, so registers hold data that's stored in the L1 cache. The L1 cache holds data that's retrieved from the L2 cache. The L3 cache holds data that's retrieved from main memory. Main memory holds data that's retrieved from secondary disk, and so on. Now, as we'll see, the reason memory systems are designed like this is that when you have this kind of system, you can access, in general, you can access your data at the speed of the fastest item at the top of the hierarchy. So that's the fastest. But with the cost of the storage at the lower part of the hierarchy. Okay, so this works all because of an idea called caching. So a cache, to a computer scientist, it's a smaller, faster storage device that acts as a staging area for the data in a larger, slower device. So just like here, you can think of your main memory as a cache for data that's stored on disk, right? You read memory from disk and then you store it in main memory. Okay, you can think of the main memory as a staging area. So once you get the data from the disk, you don't access it again on the disk, you access it in memory, which is much faster. Okay, so this idea propagates all the way up the hierarchy. Okay, so you can think of a cache. One way to think of a cache is imagine your backpack when you're getting ready to come to school in the morning. So you're in your apartment, which is kind of far away from school. So before you come into school, you take items from your house and you put them in your backpack, right? And then you come to school, and if you need those items, they're in your backpack. If you didn't do that, every time you needed something, you'd have to walk back home and get it, and then walk back to school. Right? So the idea of caching is it's a very familiar kind of simple notion, but it turns out to be quite powerful, and it shows up in all parts of computer systems. Okay, so what we say is that for each level k in the hierarchy, the faster, smaller device at level k serves as a cache for the larger, slower device at level k plus 1. And remember, our levels go from, so L0 is the highest, so the smallest, lowest level is actually the highest, the furthest up in the hierarchy. And as we increase the levels, we're going down the hierarchy. Now, why do they work? So this is a really fundamental idea. They work because of locality. So because of locality, programs tend to access data that's stored at level k more often than they access data at level k plus 1. Okay, so if we access an item at level k plus 1, we can move it up to level k. Chances are, because of locality, we're going to access it again. Okay, so now we're accessing the data at level k multiple times at the rate, at the speed of level k, not at the speed of level k plus 1. Okay, so that's the fundamental idea. And because we're not accessing data at level k plus 1 as often, we can afford to use slower storage devices, which are cheaper. Okay. And thus we can make them bigger and cheaper per bit. So what this does is the hierarchy creates a large pool of storage that's roughly about the size of the lowest level that can be accessed at the speed at the highest level. Okay. All right, let's look at how caching works in a general way. And then we'll see on Thursday how these hardware cache memories work. Okay, but like I said, caching is a very general idea that can be applied at all levels in the hierarchy. So here we have a cache. So in all kinds of, most caches, there's some kind of transfer unit to go from one level to the next. So here we have, at this upper level, we have what we'll call the cache that can hold 4 blocks. So our memory, and then at the lower level we have memory. And this memory is partitioned into blocks of some fixed size. That's the way caches near the upper part of the hierarchy work. Now, at the lower levels, like if you're accessing data, say, from a web server, then the data is partitioned into files, typically. Okay, but at upper levels, the data is partitioned into blocks. So just suppose this is main memory, and then above that we have that consists of a bunch of these blocks. So we just take the memory and partition it into blocks where each block is the same number of bytes. And then data will be transferred between memory and the cache in block size transfer units. Okay, so if you need data from the memory, if the cache needs data from the memory, it'll grab a whole block. And then at any point in time, the cache holds a subset of the blocks in main memory. Okay, so this cache is much faster, but it's also much slower. Okay. And because of that, and it's much smaller. I'm sorry, it's much faster, but it's much more expensive. Because it's faster, it's more expensive. And because it's more expensive, it's smaller. Now, suppose the cache wants to reference, say that the CPU asks for data that's contained in block 4. So it looks to see if the data is in the cache. It's not. So the cache asks the memory to give it block 4. So that block is copied from memory into the cache, overwriting one of the existing, in this case, block 8. It'll overwrite block 8. So now block 4 is in our cache. Now suppose the CPU asks for some data that's in block 10. That gets copied up, and we overwrite that block. Now, the whole idea of storing it in the cache is that we're hoping that the program that's executing on the CPU will reuse one of those blocks. We just spent all the time, we went to all this trouble to copy it from memory to this cache, and we know that's slow. So now suppose that the CPU needs some data in block B, in this case 14. Okay, so it needs a memory word that's stored, that was originally stored in memory in block 14. Well, now this cache can just return, that's what we call a hit, right? So the block that we access is in the cache. So that's good. Hits are good. Because now we can return that block directly to the CPU. And this memory is much faster than if we had to go all the way to main memory, to the DRAM. Okay, so the SRAM, much faster than the DRAM. So the CPU gets that block 14 much faster than it would have if it had just gone all the way to memory. Okay, the sort of other, the opposite of a hit is a miss. So suppose the CPU asks for block 12. The cache looks for that block, can't find it. That's a miss. So the cache has to ask the main memory, the DRAM, for block 12, where it gets copied into the cache, and then it can return that. So that takes longer, right? So the CPU has to wait for that block to be fetched from memory. And so misses are slow. So hits are good because they're fast. Misses are bad because they're slow. Now we typically distinguish between several different kinds of caches. So the first kind of miss is a cold miss or a compulsory miss, which is caused because there's just nothing in the cache. Right? Initially, caches are empty. They have no blocks. And as we fetch blocks from the lower level, from the next level, and put them in the cache will slowly fill up with blocks, and that'll increase the likelihood of hits. But when the cache is empty, we're going to miss every time, right? So there's just no way to avoid cold misses, right? So this is called warming up your cache. So as you load data items into the cache, initially it's cold, and as you add more items, you're warming it up, meaning that you're increasing the likelihood of a hit. Now, there's another sort of symmetric kind of miss, which is called a capacity miss. And these misses are due to the fact that the cache is just a certain size, right? You just can't, in the example we looked at, we only had 4 blocks. So if our temporal locality involves 8 blocks, say if the loop that we're accessing is accessing elements in an array that consists of 8 blocks, there's just not enough room to store 8 blocks in that 4-block cache. So we're going to get misses. Right? We would need a bigger cache to be able to satisfy and store those 8 blocks. And if we had a big enough cache, then we'd get good hit rate. Right? If we could store all the blocks in our cache, then the cache could take advantage of the spatial and temporal locality within that program. So in general, what we call this set of blocks at any point in time when a program is running, we call the set of blocks that are sort of being accessed over and over again the working set. And so your working set, and the working set will change as you go from loop to loop, or from function to function. But at any point in time in your program, when you have this idea of a working set, which is sort of the blocks that you need to have stored in your cache. Okay. So when your working set size exceeds your cache size, then you get capacity misses. There's this other kind of weird miss called a conflict miss, which has to do with the way that caches are often implemented. So the idea is that most caches, especially hardware caches, because they have to be simple, they limit where a block can be placed to some small set of positions in the cache. So like one of the simplest models is to just take block I can only be placed in block I mod the cache size. So in that little cache we saw that had 4 blocks, we would take block I for memory and we would stick it at block I mod 4. So block 0 would go at block 0 in our cache, as would block 4, and as would block 8. Block 9 would go into block 1 in the cache. Right? And that's, when that happens, suppose we use that model. So we're going to take block I, and we're going to put it, we can only place it in the cache at block I mod 4. Now suppose our reference pattern involves from memory block 0, block 4, and block 8. It's only 3 blocks. So we have enough room in the cache to store those 3 blocks. But because of the way we've decided to place blocks, each block will evict. When we access block 4, it'll go into block 0 in the cache. When we access block 4 in the cache, it'll overwrite that block and it'll go into block 0 in the cache. And so because of this, it's really the access pattern conspiring with the algorithm that we're using for placing blocks. Okay, so because of this, we have plenty of room in the cache, but because of this sort of the access pattern conspiring with the placement algorithm, we get misses every time. Okay. We'll see how conflict misses work in detail when we study caches tomorrow. So these caches exist everywhere in the memory hierarchy. And so all of them are caches of one form or another. Right? So you can think of the registers as a type of cache. What are they cached? 4 or 8 byte words. Okay. Where's it cached? It's cached right on the CPU itself. What's the latency? It's instant. Right? It happens within an instruction. And then who manages the cache? Somebody has to manage the cache. When there's a request to load an item from the lower level in the hierarchy, something has to decide what to do with that, where to put it in the cache. That's called managing the cache. Well, in this case, the compiler manages the cache. When you compile your C code, the compiler figures out which register data items from memory are going to go into. Okay. So TLB, this is a cache that's used in virtual memory. Then there's these hardware caches called L1 and L2 caches. So they store 64-byte blocks on modern Intel systems. And they're cached on the CPU chip itself in SRAMs that are built right into the CPU chip. And depending on whether L1 caches on Core i7s have a latency of 4 cycles, and L2 has a latency of 10 cycles. And both of these are managed by hardware. So when the CPU fetches an item from the L1 cache, hardware finds it, and if there's a miss and a block is loaded from L2, hardware in the L1 cache figures out where to put it. Okay, so all this is done without any intervention by hardware. Disks contain operating systems maintain buffer caches. So in this case, what's cached is portions of files. Okay, and they're cached in main memory. And latency to main memory is about 100 cycles or so. And these are managed by the operating system. So the operating system reserves a portion of memory to store files that you've loaded. So the operating system exploits locality. If you read a file and then start reading, referencing bytes from that file, it'll actually be served from the file cache and it won't go out to disk. Networks maintain caches. Like things like NFS and AFS maintain local caches on disk. Your browser has a cache, so when it fetches files from servers, it stores those files locally on disk. So if you reference those web pages again, they're served from your local disk rather than going all the way across the network. Okay, so the point is that these caches exist everywhere in the memory hierarchy. And they're all based on the same principles. They're just implemented in different ways. Okay, so just to summarize what we've done today, we've seen that there's a gap between the CPU and our storage devices that continues to increase. We've seen that well-written programs have this property called locality. And we've seen that caching, by using caching, we can build a memory hierarchy that takes advantage of locality in programs and allows us to build storage systems where we can access data at the rate of the fastest device, but at the cost and capacity of the devices at the lowest level. Okay? So Thursday, we're going to look at a very specific part of the hierarchy called cache memories.